Hello students, in the previous classes we have discussed the concept of DC machine as DC generator. Today we will see that how exactly the DC motor works. So we know that the constructional features of DC generator and also the DC motor is same, but DC generator works on the principle of Fleming's right hand rule. DC motor works on the principle of Fleming's left hand rule. Fleming's left hand rule determines the direction of current carrying conductor in the fixed magnetic field. We know that the motor is used to convert the electrical energy into mechanical energy, and also it works on the principle whenever the current carrying conductor is placed in the magnetic field, a force is set up on the conductor. So I already explained to you with this armature slots, and here the armature is slotted in the outer periphery. Here we are going to place the conductor. So when this is kept in the magnetic field, so in the first class I explained how exactly the pole structure is. This has two parts. This is pole shoe and then this is pole core. Here we are going to wound the coil. So suppose this is the north pole and this pole is south. So here we are going to connect the coil. Then we are going to connect the coil continuously, that is with respect to the another pole. Here whenever you are giving the excitation voltage, that is DC voltage, the field lines will set up in this air gap. So here since the conductors are placed, whenever these conductors are placed in the magnetic field, a force will be exerted. So what will happen when the force is exerted? There will be a movement of this rotor. So that is why this is called it as the rotating part. The armature is called it as the rotating part, it is called it as rotor. So this concept we are using in the working principle of DC motor, and the direction of conductor motion is represented by the thumb of this left hand. So we are going to stretch this thumb, forefinger and middle finger at right angles to each other. This thumb represents the motion of the conductor, then forefinger represents the direction of the magnetic field, and this middle finger represents the conventional current direction. This is how we are going to find out the current direction by using Fleming's left hand rule. Now we know that the DC motor converts electrical energy into mechanical energy. To this, when the DC supply is given, this Vt represents the applied voltage. This has the polarity plus and minus. When this supply is given to the DC motor, so here what will happen, due to that magnetic field and the conductor kept in the magnetic field, the force will be experienced, and also according to this Faraday's laws of electromagnetic induction, what will happen, the EMF will be generated. So that EMF generated is directly proportional to N d phi by dt. As we seen in this equation, the EMF induced in the conductor whenever there is a flux linkages changes. So the change in flux linkages we are representing as N d phi by dt, where N phi represents the flux linkages. And we are also representing this equation is equal to minus N d phi by dt. The generation of EMF mainly depends on the Faraday's laws of electromagnetic induction. And also here I have represented this is minus N. According to Lenz's law, the response opposes the cause. Here the response is the EMF, this opposes the supply voltage, that is why it is called it as back EMF. And then this electrical power is converted into mechanical power at the load. At the later stage I will explain to you mathematically how exactly this electrical power is converted into mechanical power. So here we are using the symbol EB for back EMF, Vt is the applied voltage, T DEV developed, that is torque developed in the motor we are representing as TDEV, and then torque of the load, it opposes this torque developed by the armature. So, that is why we have shown this with the opposite direction. So, and then the input electrical power to the DC motor here, see the EMF induced, the back EMF induced is EB multiplied by the current IA will give you the electrical power to the DC motor. So, here due to this, and also we know that in case of motor there are two types of windings. One is the series field winding, another one is the shunt field winding. So, we are representing this series field winding with less number of turns. And we have one more winding, that is shunt field winding. This is of more number of turns of thin coil. This is of less number of turns of thick coil. Since we are using the series field winding that is connected in series with the armature, so what we are doing is to make the current to flow properly, we are keeping this resistance of the winding that is very less. We know that resistance is equal to V by I. So, resistance R is inversely proportional to current I is inversely proportional to resistance R. When the resistance value is less, the current flow will be better. So, that is why we are using that thick wire of the length will be less, because the equation of resistance that will be equal to rho L by A. When the length is less, the resistance will be less. When the area is more, the resistance will be less. That is why we are using for series field winding the less number of turns means the length is less and then the thickness is more. So, in this case the resistance will be less. When the resistance is less, the current flow will be better. In case of this shunt field winding, so here we are considering R is equal to V by I. This we are going to call it as voltage coil. Series field coil we are going to call it as current coil. We have to have this voltage across this shunt field coil should be more. See here, R is directly proportional to voltage and voltage is directly proportional to R. To make this resistance more, what we are doing is we are using that long length wire of thin coil. So, more number of turns is there and it is of thin dimension. So, now what will happen? R is equal to rho L by A. Here area is less, then the resistance will be more, and length is more, the resistance will be more. That is why we are using this is more number of turns of thin coil for shunt field winding, that is voltage coil, and less number of turns of thick coil for series field winding. This is also called it as current coil. Now, what will happen when current flowing through this series field winding, that is ISC, this produces flux phi SC, and when the current flowing through this shunt field coil, this also produces the flux, this will be phi SH, or we can consider that phi 1 and phi 2 also. Okay. When there is an interaction between these two fields, what will happen? The torque will be produced due to the interaction of two flux fields. So, the torque will be produced. This we are going to call it as the twisting moment. So, that is what here we have represented. The electrical power to the DC motor EBIA is equal to Ka phi omega m Ia. This omega represents the speed. Here phi and Ia. Phi is the flux due to the shunt field current ISH, and then always the flux will be directly proportional to current. So, here we can say it is phi is directly proportional to ISH, and also one more current is there, that is the part of the armature. Okay. Since armature is connected in series with this, ISC will be equal to IA. Due to the interaction of this phi SC, means this is current IA is directly proportional to phi SC. Here we have represented this phi SH, that is due to ISH, as phi. That is why you have in the torque equation, that is phi and IA in this, that is equal to torque developed into the speed. This we are going to call it as the output mechanical power to the load. This is how the electrical power is converted into mechanical power by the concept of DC motor. So, now you see the definition of this back EMF. I already told you that here the back EMF is the response and voltage applied is the cause. The back EMF opposes the voltage, means the generated EMF opposes the voltage, that is why it is called it as back EMF. The induced EMF in the rotating armature conductors always acts in the opposite direction of the supply voltage. This is according to the Lenz's law. Lenz's law says that the response opposes the cause. The supply voltage is the cause in this case, and EB is the response. EB opposes the supplied voltage. Next, we will see that what are the different types of DC motors we have. As you have seen in the DC generator, here also we have separately excited DC motor, self-excited DC motor. In self-excited DC motor, we have the another categories, that is series DC motor, shunt DC motor, compound DC motor, depending on how exactly the series field winding and the shunt field winding are connected with armature. So, and also we have classified this compound DC motor as differentially compound and cumulatively compound. So, this is depending on, that is the flux produced in the series field winding and the flux produced in the shunt field winding. If both are in the same direction, then we can consider it is the additive action, that is called it as cumulatively compound motor. If the direction of flux produced by the series field winding and the direction of flux produced by the shunt field winding, if both are opposite to each other, then we will consider it is differential compound motor. So, now we will see one by one. First, you consider this separately excited DC motor. As the name indicates, you see that the field coil is excited separately, that is by using that voltage, DC voltage VF. So, when the field coil is excited, what will happen? The current ISC will flow in this coil. So, the internal resistance of the coil. So, always the resistance of the coil will be less. So, you can represent this with respect to this coil itself like this, or otherwise you can represent with the separate resistor connected in series with the coil. So, you can represent either in this manner, here itself you can represent RSC, or otherwise you can represent this coil with the series resistance. This represents RSC and this is the field coil. If you are not writing this separate also, you can understand that this has some small resistance. Here we have the armature resistance RA, and we know that the motor converts electrical energy into mechanical energy. See here the electrical supply is given, that is the VT is the DC source, this is applied. See the direction of current. So, this is from DC supply to the armature. Here the back EMF EB generated, then this opposes the applied voltage VT. Here the field is excited separately. So, that is why this is called it as separately excited DC motor. The field equation, what is the voltage across this field? Vf is equal to RSC into ISC. The current flowing through this series coil multiplied by the resistance will give you the voltage across the coil. Similarly, in armature equation, EB is equal to, you apply the KVL in this, EB is equal to here rise in voltage from lower potential to upper potential. So, here upper potential to lower potential in case of generator, since you are considering the current direction in this manner. So, you have to consider, if you are considering in this direction, it will be the lower potential current leaving at the upper leaving at the entering at the upper potential and leaving at the lower potential, means this will be plus and this will be minus. Here in this also this is minus and this is plus. According to that, when you are applying the KVL, EB is equal to Vt minus IaRa. This IaRa represents the resistive drop in this armature. This EB can be represented in terms of phi and omega m, because here we have the equation. I already told you that this generated equation, that is equal to Zn phi p divided by 60A, where Z represents the number of conductors, N represents the speed in terms of RPM or RPS, revolutions per minute or revolutions per second. So, since we have divided this by 60, we will consider it is in terms of RPM, and then flux is the flux per pole in Webers. This P represents the number of poles, A represents the number of parallel paths. It is depending on the lap connected machine or wave connected machine. In case of lap connected machine, A is equal to P. In case of wave connected machine, this A is equal to 2. So, now the equation for this generated EMF and also the back EMF will be same. This is equal to Zn phi p divided by 60A. Here the Z is constant and then P is constant, A is constant, 60 is constant. Only thing is this EB is directly proportional to the speed and flux. As current increases, this flux increases, as current decreases, this flux decreases, and also this speed is variable in this case. That is why EB is directly proportional to N phi. Here the speed we have represented in terms of, this is the angular velocity, because we are considering the rotation of the armature. We are considering this is angular velocity or angular speed. We are representing this in terms of radians per second. Okay, this speed is represented by omega, and this is the flux per pole. EB is directly proportional to speed and flux per pole. That is why we have represented EB is equal to this Ka is the proportionality constant, omega into phi. So, that is what this equation, EB is equal to Ka into phi omega m. So, because of this you are considering this equation. Now, we will see how exactly the self-excited DC motors works. In case of self-excited DC motors, the classification is done according to the connection of series field winding and shunt field winding with respect to the armature. You see that this is the DC motor. Here the series field winding is connected in series with the armature. Here we have represented the series field winding with the equivalent resistance, that is RSC. The armature resistance is represented as RA. See, the supply is given, the motor converts the electrical power into mechanical power. So, the supply is given, current flowing, the current flow direction is in this way, okay, current is entering to this. So, EB is generated, this EB opposes the supply voltage. So, the terminal voltage equation, sorry, supply voltage equation Vt is equal to EB plus, see, EB plus Ia, since the same current is flowing through this RSC and RA. So, the drop across this resistance RA and drop across this resistance RSC, we have to consider it as additive. So, Ia RA plus Ia RSC is the voltage drop across this series field winding and also this armature resistance. So, this is the equation for series motor. This is how we are connecting the series field winding in series with the armature in case of DC series motor. And this is, I already told you, this EB is directly proportional to speed and this current. So, here flux we have represented in terms of current, because this current IA is flowing through both the windings, that is armature winding. Here armature AA is connected in series with the series field coil. Since IA is flowing through this, due to the supply voltage, what will happen? This flux produced is directly proportional to IA. That is why this flux representation we have considered this, and this is also proportional to IA. That is why we have the two proportionate constants, that is K1 and K2. EB is equal to K1 K2 IA omega. Now you consider this shunt motor. Here, as the name indicates, it is shunt, means parallelly you have to connect. So here shunt field winding is connected in parallel with the armature. So in this, the supply voltage V is the voltage across this shunt field coil, that is ISH into RSH, that is represented in this. VT is equal to ISH into RSH. You see this, the current I supplied by this source at this junction, according to KCL, Kirchhoff's current law, the current entering the node is equal to sum of the currents leaving the node, that is IL is equal to ISH plus IA, that is represented in this equation. Then VT, when you are applying KVL to this loop, so VT is equal to EB plus IA RA. EB plus IA RA will give you this supply voltage. So these are the equations, main equations for shunt motors. Now we will see how exactly the electrical power is converted into mechanical power mathematically by using the equations. Here we have seen that VT is equal to EB plus IARA. Multiply both sides of this equation by IA. So when you are multiplying that equation, that is LHS and RHS of this equation by IA, you are going to get this equation. You see that VIA, what is this? This is the input given to that motor. You see that here this is the VT is equal to, see here the input current to this motor is IA. So VT into IA is the electrical input to a armature. The voltage across this terminal, and then due to this voltage the current IA is entering to this armature. This is the electrical input to a armature. Then EBIA, this is the electrical equivalent of mechanical power developed by the armature. This EB opposes the supply voltage. Then what is this term IA square RA? As we see in here, we can say that this is the copper loss. Where exactly this is occurring? So this electrical, that is copper loss, is occurring in the armature conductors. That is why it is called it as armature copper loss. So now you see that whatever you are generating, you are giving as an input, you are not getting at the output. So there is some loss. So that is why the motor develops mechanical power that is equal to VTIA minus losses. So this is the electrical input to a armature, and then there is I square RA loss in armature. So electrical input minus losses will give you the mechanical power develops at the motor. So now when exactly this mechanical power will be maximum? To see that one, you differentiate this equation with respect to IA, because current IA is variable in this. So you differentiate this mechanical power equation with respect to armature current. When you are differentiating this equation, this is VT minus 2IA RA equated to 0. And then from this equation, so you will get that IA RA is equal to VT by 2. Substitute this IA RA is equal to VT by 2 in this equation, you will get, that is EB is equal to VT by 2. When exactly we are going to get that maximum power delivered? So when the back EMF is equal to half of the supply voltage. This is the condition for maximum mechanical power. Now you see that how exactly we have considered the connection of series field winding and shunt field winding in case of compound motors. So, as we see here, this series field winding is connected in series with the armature. Across that series combination we have connected shunt field. This looks like that long shunt compound generator. See here, the apply voltage is given here, and then IL is equal to ISH plus IA according to Kirchhoff's current law. So, now VT is equal to EB plus IA, that is RA plus RAC. This is the voltage drop across the armature resistance and the series field winding, and then VT is equal to ISH into RSH. This is how you are considering the compound motors, but you are going to classify this compound motors according to the flux produced by series field winding and flux produced by the shunt field winding are additive or subtractive. Depending on that, you are going to classify the compound motors as differential compound and cumulatively compound. In both the cases, you have long shunt and short shunt. Now, I will explain to you how exactly the series field windings and the shunt field windings are connected in differentially compound and cumulatively compound motors. So, we have armature, this is the motor, terminals AA. If the series field winding is connected and shunt field winding is connected across this in this manner, and then the supply is given in this VT, this is plus minus, then current I is supplied from the source. So, this will be ISH and this is the current IA, that is equal to ISE. So, here in this case the flux produced by this series field winding and the flux produced by this shunt field winding both are additive. This is called long shunt, cumulatively compound DC motor. In case of differentially compound, what will happen is this terminal of these windings are reversed. Means here the flux produced by the current flowing through this series field winding and the flux produced by the current flowing through this shunt field winding both are opposite to each other. So, now the flux as are, this is subtractive. This is called differentially compound. This is, as we have connected the shunt field winding across the series combination of this series field winding and the armature, this is differentially compound long shunt DC motor. When you are considering that short shunt, what exactly you are doing is you are connecting this shunt field coil only across the armature. This is called, now this is the terminals Z, Z, Z. So, if it is in this manner Y, 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 this is cumulatively compound short shunt DC motor. If these terminals are reversed, this is Y, Y and then Y, this is called differentially compound short shunt DC compound motor. So, this is how we are going to differentiate the differentially compound motor and cumulatively compound motor. So, by the connection of this series field winding and shunt field winding. So, now you see that how exactly the torque is produced. I already told you that there are two fluxes generated, one is due to the current flowing through the series field winding, another one is due to the current flowing through shunt field winding. So, I already represented in this, the conductors are placed in this, the conductors are placed in these slots. The armature is slotted in the outer periphery, the conductors is placed in this slot, okay. And the conductors under the influence of north pole, we are going to connect it to the conductor under the influence of south pole to get that positive and negative polarity, okay. So, now here you see that you consider the conductor of radius r. When it is placed in the magnetic field, a force will be exerted. That I will explain to you, but the radius of the conductor is not of this much, this dimension you won't get this much radius, but it will be of lesser. But I took this as an example. When the force experienced in this means I will apply the force by using this pen. You see that it will move, it will have some movement in this like it will rotate. If I exactly apply the force tangentially, what will happen? This is going to rotate, okay. So, this is called twisting movement or turning movement. This is the torque, okay. So, how exactly here I am applying the force by using my finger, but there in the DC motor, when the conductors are placed in the magnetic field, the force will be exerted. That force will make this to move, okay. So, that is due to the interaction of two fields. So, this is called the torque or twisting movement. So, the definition of torque, you see that the measure of causing the rotation of a wheel or the turning or twisting movement of a force about an axis. It is rotating about its axis, no? About its own axis it is rotating when I am applying the force. It is measured by the product of this force what I am applying and the radius, okay. It is the product of force into radius. Now, this I explained, and also it is having some speed, no, that is depending on how much force it is exerted on this, okay. The speed of this rotation depends on the speed, that is we are representing in terms of RPS, that is revolutions per second. Now, you see that how exactly we are deriving the torque equation. So, I already told you that the equation of torque is the product of force and radius of the conductor. This is explained in terms of or expressed in terms of Newton meters. Then, due to that force, work done by this force in one revolution. So, to rotate that one full revolution, when you are going to consider what is the periphery of this circle. The periphery of this circle is 2 pi r. So, that is why in one revolution means one full periphery we have to consider. The work done by this force in one revolution is equal to force into distance, that is F into 2 pi r. This is expressed in terms of joules. Then, to represent this work done per second, what we have to do? We have to multiply by this speed, that is force into distance into speed, that is joules per second. So, if you are expressing in terms of RPM, this has to be divided by 60. So, then separate the terms, that is F into R, because F into R is the torque. You can represent the work done in terms of torque. That is why you separate these terms, that is F into R multiplied by 2 pi n joules per second. And we are expressing this speed in terms of angular velocity omega. When we are representing this n in terms of angular velocity omega, so you have considered this 2 pi n. So, it is in terms of radians per second. Now, what will be the torque equation? We have the torque is equal to F into R. Now, substitute this F into R is T in this equation. So, and 2 pi n is omega in this equation. So, now work done per second is equal to torque into angular velocity in terms of radians per second, torque is in terms of Newton meter. So, you are going to express this work done in terms of joules per second. The power developed is equal to, that is torque into omega, it is in terms of watts. Now, we have two types of torque, one is armature torque, another one is shaft torque. The shaft torque will be always less than the armature torque. Later, at the later stage, I will explain to you how exactly the shaft torque is less than the armature torque. First, you see that how exactly we have deriving equation for armature torque. let TA, this suffix A represents the armature torque. You consider this is torque developed by the motor armature in terms of Newton meter. We know that the speed we are expressing in terms of RPS. So, if you are expressing in terms of RPM, we have to divide this by 60. If we are expressing this speed in terms of angular velocity, this is omega is equal to 2 pi n radians per second. Then we have that power developed, P is equal to TA into omega. We can represent this omega in terms of 2 pi n. P we are representing in terms of watts. The electrical power converted into mechanical power in the armature. So, that is equal to EB into IA. I have already explained that concept, how exactly the electrical power is converted into mechanical power. Electrical power we are expressing in terms of the applied voltage multiplied by the armature current. Then mechanical power, that is back EMF into armature current, that is equal to EB into IA in terms of watts. See here, the power developed is TA 2 pi n watts, and the mechanical power you are expressing in terms of back EMF as EBIA. You can equate these two equations. So, now when you are equating this P and this EBIA, you will get this. And also we know that the generated EMF EB is equal to Zn phi A, Zn phi P divided by 60A. Substitute this, that is Zn phi P divided by 60A in this equation. See, now TA into 2 pi n is equal to Zn phi P divided by 60A into IA. So, now you separate the terms here, you get only this torque equation in the left hand side. When you are considering that, this 2 pi n will come to the right hand side. So, now you are getting this is Z, here Nn will get cancels out. So, phi ZIA divided by 2 pi into P into A. So, now you can get this TA is equal to 0.159 phi ZIA, that is multiplied with P by IA in terms of Newton meter. So, finally, when you are going to convert this Newton into kg, you have to divide this equation by 9.81. So, when you are dividing this constant value by 9.81, you will get TA is equal to 0.0162 phi ZIA multiplied with P by A. This is in terms of kg meter. We know that here from this equation you see that here this is the constant value 0.0162, and then here the number of conductors are constant, number of poles are constant, number of parallel paths are constant. It is depending on the lap wound or wave wound. Only variable quantities in this is phi and IA. That is why we can represent the torque developed in the armature, TA is directly proportional to flux into IA. For a series motor, TA is directly proportional to flux into IA square. So, that is for shunt motor, TA is directly proportional to IA. So, here this is not flux into IA square, this is TA is directly proportional to IA square, because flux is directly proportional to IA. Since this TA is directly proportional to flux into IA, we can say that TA is directly proportional to IA into IA, because flux is directly proportional to IA. There is a small typing error in that, TA is directly proportional to IA square in series motor. This IA into IA will give you TA is directly proportional to IA square. In case of shunt motor, flux is constant, because you are keeping ISH constant, because RSH means shunt field coil is connected across the this applied voltage V. So, that is why this ISH is constant. Since ISH is constant, flux is constant. So, this is the constant term in case of shunt motor. So, that is why TA is directly proportional to only IA in case of shunt motor. So, this is the torque relationship in case of series motor and shunt motor. Now, you see that how exactly the final equation of this torque equation of the armature we are getting. here I already told you, here you have that TA into 2 pi n is equal to EB IA. So, in that equation, when you are finding this TA, this will be 1 divided by 2 pi EB IA divided by n. So, when you are substituting this value, pi is equal to 3.14 and you are getting this 0.159 EB IA divided by n. This is in terms of Newton meter. When you are converting the torque in kg meter, you have to divide this equation by 9.81. Finally, you are getting this TA is equal to 0.0162 multiplied by EBIA divided by n in terms of kg meter. If n is in RPM, the armature torque, you are going to get, this is n, you have to divide by 60. This is TA is equal to EBIA divided by 2 pi n by 60. So, this will be 9.55 EBIA divided by n. It is in terms of Newton meter. Now, TA you can express in terms of number of conductors, IA and phi, this number of poles and number of parallel paths. If you are expressing in terms of this equation of TA is this, or otherwise if you are expressing in terms of EBIA and n, this TA is, you have to use this equation. So, this is how you have the two equations for armature torque. Next you see this, what is this shaft torque? The torque which is available at the motor shaft for doing useful work is called shaft torque. We know that armature is connected to the shaft in this. So, armature is connected to the shaft along with that commutator, split rings, end rings and also with that brushes. So, the torque which is available at the motor shaft for doing useful work is called shaft torque. The total torque, that is TA, that is the torque developed at the armature, is not available fully available at the shaft. As part of it, there is a loss in overcoming the iron losses and friction losses. Therefore, TSH is always less than this TA. So, output is equal to TSH into 2 pi n. So, when you are considering this equation, output is equal to TSH into 2 pi n, that is the power. Now, TSH in Newton meter, when you are expressing and when you are considering n is in RPS, the TSH equation will be output divided by 2 pi n. When you are considering this n in RPM, you have to divide the 2 pi n by 60. So, now TSH is equal to 9.55 into output in watts divided by n. This TSH you are expressing in Newton meter. When you are expressing in kg, you have to convert or you have to divide this equation by 9.81. Then you will get the torque in terms of kg meter. Okay, this is about the torque equations. I already told you there are two types of torques. One is armature torque, another one is shaft torque. Now, you see the equation of a DC motor, that is speed equation of a DC motor. So, up to this we have seen that how exactly we have derived the equation of torque for armature and also the shaft. Now, you see that there are different types of motors. We have already seen that there are different types of DC motor, that is separately excited DC motor and self-excited DC motor. In self-excited DC motor, you have series motor, shunt motor and then compound motor. You see that how exactly you are going to get the speed of DC motor in all types of motors. We know that we have that back EMF EB is equal to V minus IARA. The back EMF means the generated EMF is not exactly equal to the applied voltage. Since there is some drop across the armature resistance, we are getting this EB is equal to V minus IARA. And also we know that the equation of this generated EMF EB is equal to Zn phi p divided by 60A. When you are substituting this Zn phi p by 60A in this equation, you are getting that is equal to V minus IARA. Here that speed component is there. Now, you have to find out what is the equation for this speed in terms of this applied voltage, then the armature voltage drop and then number of conductors, flux per pole and then number of poles and also the number of parallel paths. Now, when you are considering this n in LHS and transferring all the parameters to the right hand side, you are going to get this equation. So now we have already know that V minus IA RA is equal to EB. So here in this term, when we have separated this, you have that EB. So this will be, when you are substituting V minus IA RA, that is equal to EB, you will get that N is equal to EB by 5, that is multiplied with 60A divided by ZP in terms of RPM. Since in this case, here when you are observing 60 is constant, the number of parallel paths are constant, the number of conductors are constant, and P is constant. So here what will be the variable? So only this EB and phi are variable. Now N is directly proportional to what? The speed is directly proportional to EB divided by phi. And we have represented this N is equal to K into EB divided by phi, where this K represents the constant of proportionality. So that is why you have that equation N is equal to K into EB by phi. Thus, speed is directly proportional to back EMF and is inversely proportional to flux per pole. Now, we will express this speed relationship with EB and phi for DC series motor. First you consider this N1, IA1 and phi1 be the speed, armature current and flux per pole in the first case. In the second case, when the current is increased, N2, IA2 and phi2 be the speed, armature current and flux per pole in the second case. When you are using the relationship, that is N is directly proportional to EB by phi, so what will happen? N1 is directly proportional to EB1 divided by phi1, where EB1 is V minus IA1 RA. Similarly, N2 is directly proportional to EB2 divided by phi2, where EB2 is equal to V minus IA2 RA. When you are dividing this N2 equation by N1, that will be N2 by N1, that is equal to EB2 by EB1, that is equal to phi1 divided by phi2, because N1 is directly proportional to back EMF and N1 is inversely proportional to phi1. That is why this is not multiply. So you can say it is equal to, sorry, here I have used that multiplication sign. So this is equal to the relationship you are going to get, it is N2 divided by N1, that is equal to EB2 divided by EB1, and then since it is, so here you are going to get this is phi1 divided by phi2, and we know that phi1 is directly proportional to current IA. When you are expressing that equation in terms of currents, in terms of armature currents, since phi is directly proportional to IA, N2 divided by N1 is equal to EB divided by EB1 multiplied by IA1 divided by IA2. This is the speed equation in case of series motor. And in case of shunt motor, since flux is constant, this phi1 is equal to phi2. So what will happen? Since phi1 is equal to phi2, this will get cancels out. Thus N2 divided by N1 is equal to EB2 divided by EB1. These are the speed equations in case of shunt motor. Okay. So you have seen, we have derived the equation for torque and also we have derived the equation for speed in different types of motor. In the next class, I am going to solve the problems on back EMF and torque. Thank you.